start. First of all, thank you, Zhang. Thank you so much for taking the time during the Easter break to give this Turing seminar. It's really a great pleasure for me and my colleagues to host your talk. So Zhang is faculty at CISPA, Helmholtz Center for Information Security in Saarbrücken. He has a PhD from the University of Luxembourg about 5 years ago, I think. And he's been doing really great work at the intersection of machine learning and privacy. As one of the most prolific authors in the field. He's been publishing in all top conferences in security, and also conferences like DAB, and he's in pretty much all the program committees of these conferences nowadays. Yeah, without further ado, today is going to talk about quantifying privacy risks in machine learning. The virtual floor is yours. Let me just start the recording and then you can go. Thanks, Zhang.
All right, great. So thanks for the nice, yes.
All right, please.
All right, so thanks for the next introduction, Emiliano. So I'm Zhang, and today my topic is quantifying privacy risks of machine learning models. So, wait. Okay, right. So first, a little bit about me. So I'm currently a faculty member at CISPA Helmholtz Center for Information Security in Germany. My research interest is mainly on the machine learning, security, and privacy. I also work on social network mining, also fairness. Also recently, I started to work a little bit on online hate speech, which is powered by iDrama Lab. The content of today's talk contains 3 parts. I will first talk about the membership inference. Then I will talk about data reconstruction in the online machine learning setting. And then I will talk about our new work on link stealing attacks against graph neural networks. So let's get started. Membership inference. So actually, membership inference is one of the most, let's say, popular attacks against the machine, most popular privacy attacks against machine learning model nowadays. So when we start talk about we are in the era of machine learning. So I think I'm not telling you anything new. So machine learning nowadays has been actually used in many domains or areas in our lives. For example, this driverless cars, facial recognition, or your Amazon Alexa at home, or social networks. So the reason machine learning models has achieved so much advancement is mainly due to the large-scale, high-quality data nowadays has been digitalized or collected. However, many cases, machine learning models are trained on data that can be sensitive. For example, biomedical data, such as doctors actually nowadays using your biomedical data actually to train classifier to do some diagnosis, or even your keyboard input on your smartphone. So nowadays, if you're using a smartphone, you're using WhatsApp. So basically, if you use it longer and longer, you realize that the auto completion of the keyboard typing is better and better because actually they are using your data to gain more and more information and train the model better. So on one hand, this is great because now the machine learning model become way more powerful. So our life become much more easier. On the other hand, so we will have a big privacy issues. Imagine if you have a trained machine learning model that's able to leak its underlying data, which are sensitive. In this sense, in the end, they will cause severe privacy consequences. So my research topic actually centered around this area, that is quantifying privacy risks of machine learning models. And we will start with membership inference. So before I go deeper of membership inference, I will give a very naive baseline or pipeline of how machine learning works nowadays, at least in labs. So to do machine learning nowadays, all you need to do is, I don't know, 3 steps. First step, you need to download data set from the internet. The second step, you open your favorite library, like PyTorch or TensorFlow or Keras, and choose your favorite model. Then you throw the data to the model, you train the model. So to test how good your model is, or to test, whether your trained model is useful or effective, all you need to do is just throw another sample. You can call it a testing sample. In this case, for example, this panda image. You throw this image to the model, and then the model will give you a prediction. Yeah, let's say in the most common machine learning setting, which is a classification. What this means is you will get a 3-dimensional vector. We call it a posterior probability, or actually you can also call it prediction confidence score. Yeah, this says, let's say 80% this image is a panda, 10% is dog, 10% is a cat. So that's basically how nowadays generally machine learning works, very naively. Yeah. So what is membership inference here is actually I want to know whether this panda is in the original training data set of the machine learning model. Yeah, so it's actually a binary choice. I want to know whether you're a member or not. And all I have, the information I have from the target model is only the black box access. What this means is that I can only throw the panda to the machine learning model. Model will give me the output, and then I can only use this output to judge whether this image is part of its training data set or not. So I will talk about our paper nowadays. It's already 2 years ago, actually. So NDSS 19 paper, ML leaks. So we are not the first one to propose membership inference attacks. I think one of the first talks in this this seminar series is by Professor Vitaly Shmatko from Cornell Tech. And actually, he is the one who proposed the first attack in membership inference. So I will give you a quick recap of how that attack works. So in general, you have a target machine learning model, you have a data set, and then you have an attacker. So what the attacker has is a data set that's coming from the same distribution as the target model, the training data set. And then what the attacker does is the following. So he split data to training and testing. And then he used the training to train a set or bunch of shadow models. So here, the shadow models is the shadow of the target model. What this means is that if the target model is, let's say, it's a 3-class classification, shadow model is 3-class classification as well. So you also assume you have the same structure. Yeah. So basically, so you are basically imitate or mimic the behavior of a target model. Once you train the shadow models, and then you throw the training and testing inside the shadow models, you will get a bunch of output or posteriors. I will use posteriors a lot in this talk. So basically just the output of machine learning classification models. So we have a bunch of posteriors, and then I will label them. So because here you can see training here in the shadow model setting, training here actually is the members, because these are the members, these are the data that are used to train the shadow models. Yeah, and testing actually is non-members. So you see all this process I'm doing here is actually generating data set, generating training data set. Sorry, so generating training data set to train the attack model, membership inference attack model, which is a binary classification. An image can either be a member or non-member. Okay, so once my attack model, actually a bunch of attack models are trained. So in the end, I still want to know whether the panda image is part of the training data set or not. So what I do is I throw the panda image to the target model. The target model will give me an output, will be another posterior. I throw this posterior inside the attack model. Attack models will tell me if this is a member or not. So basically that's a recap of how this first membership inference attack works. So actually, so before I go deeper for what we did on top of this model, on top of this attack, so one reason you can see that the reason that membership inference can work, or the signal of membership inference, mainly related to overfitting. Because here you see all the posteriors labeled with this red background. Actually, they are member samples, and the blue background are non-member samples. For the red background posteriors, you see they always have one class that is quite confident. Yeah, and on the other hand, for the blue ones are non-members. Normally, the 3 classes, the confidence are more or less similar. So that's the information that the attack model could leverage to actually make the membership inference work. All right, so this is an attack by Professor Shmatko at Cornell. So, however, this work makes several key assumptions. The first one is they assume the attacker or the adversary has a data set that's coming from the same distribution as the target model. Yeah. Second, they have to train a bunch of shadow models and attack models. So which means with all these assumptions together, the attacker is hard. The job is hard for the attackers, which means the attacker need to spend more resources to train multiple shadow models, multiple attack models, also need to get a data set that's coming from the same distribution as the target model's original training data set. So since this is all big assumptions, which means that the attack will be less efficient, if we are able to relax all these assumptions, the attacker's job is much easier. If the attack job is much easier, then the membership inference threat is become more obvious. So that's basically what we did in this paper. So we basically follow this direction. So we did 3 attacks. In our first attack, is actually a very simple modification. So instead of using multiple shadow models, multiple attack models, I would just use 1 shadow model and 1 attack model. Okay, so nothing else changed. Also, I still have the assumption that I have the same data set coming from the same distribution as the target model training data set. So let's quickly see some results. So the green bar is our result, and the blue bar is the original work result. So left is precision, right is recall. So remember, membership inference is a binary classification. So I'm using precision recall here. You can see in almost all cases on probably 13 data sets, we almost achieve similar performance. This means that 1 attack model, 1 shadow model are enough. Yeah. But that's not the key assumption we want to relax here. So key assumption we want to relax here is still the data set coming from the same distribution. So what we do here actually is the following. So we simply, so it's also quite simple actually. So we simply replace the shadow data set to a completely different data set. So how different this is? How completely different it is? For example, the target model can be an image data set. A target model can be trained on image data set. Our local model can be trained on natural language processing data set. It's just pure text. Yeah, the target model is images. My local model is just pure text, strings. Yeah, and then I just do the same procedure as the previous one. I mean, as the previous attack. In the end, I get my attack performance. Okay, so that's basically what we did. So in this sense, since your local data set is also different from target model, also very likely the local shadow model have the different architecture from target model. So in that sense, we also implicitly relax the assumption of the shadow model have the same architecture as the target model. Let's quickly see some result. Left is precision, right is recall. On the diagonal are the original first attack result. We are using the same data set to attack the same data set, right? So on the other hand, everything off the diagonal actually is the transfer attack, which is, for example, I'm using Sapphire 100 to attack a news data set. Sapphire 100 is an image data set, and news is actually a natural language processing data set. It's just a text. You see, in many cases, actually the performance is pretty good. Performance is pretty good. I'm not saying that this will always work. You can use any data set to do it, but in general, many cases, you can use a different data set to achieve a similar performance as the result on the diagonal. So why this happens? So why this happens? Just remember one thing, the input to the membership inference attack model is not the data sample itself. Instead, it's the target model's output as the input to the attack model, which means in here, actually it's the largest 3 posteriors of the target model on this sample you are interested in. So here I make a TSNE plot here. So this is 2 dimensions. So the blue circle is the member sample for Sapphire, and the blue cross is the member sample for news. You can see that as similar cases, the red part are Sapphire's non-members and the news dataset non-member. Again, this dataset, one is image, one is natural language processing datasets, completely different datasets. So you can see that if you do this TSNE embedding, you can see the members of these 2 datasets are more or less aligned in the same area, yeah, in this 2D space. So as the non-member case. So what this means is that if I'm able to learn to separate the member for Sapphire 100, if I learn to separate Sapphire 100 member and non-member, this decision boundary, which is the decision boundary of the attack model, can be automatically carried out to separate the data set of the member and non-member of news data set. Okay, so more generally, so here, this attack sounds weird or sounds absurd, but actually what we did here is we didn't transfer the data set itself, but we transferred the overfitting behavior. Or in another way, if 2 models are both overfitted, their behavior are similar if they see member samples versus non-member samples. That's basically how this second attack works. So now let's go to the third attack. So can we make it even easier? So I keep on mentioning that the overfitting is the main reason for membership inference to work. So in our third attack, we just get rid of all the shadow model training and attack model training. All we did is we throw the panda inside target model. I get a posterior, and this posterior, I will develop a new threshold picking algorithm And if, let's say, the largest posterior is about 0.7, I consider this image as a member. That's it. Yeah, this is basically the simplest attack you could do out there for membership inference. Now let's combine all the three attack performance together. So you see that the left again is precision, the right is recall. You see in most cases on all the 13 data sets, adversary 1 and adversary 2 are more or less similar performance. So for the adversary 3, which I only find the threshold for that attack, actually you see the left figure, the precision is a bit low. However, on the right side, the recall is much higher. So if I further tweak the threshold picking algorithms a bit, in the end, the performance is also almost a bit similar. Yeah, so it's still not as good as 1 or 2, but still it's very comparable. Actually, it's like a 3% difference. So just remember one thing, that the attacker 1, 2, 3, each of them are simpler than the previous version. And attacker 1 is actually simpler than the original membership inference attack. So what we show here is actually, even you have less assumptions, membership inference can still work. Yeah, so which means that this attack can be practical. So this is the first work I want to talk about today. So another thing I'll talk about today is, okay, I got a question, I guess, so I will quickly answer this. What is the application of having data from distribution for training the attack model, please? Given the attacker aim to know if the data is a member. What is the application for having data? I do not follow your full question. So because here is the data is from the same distribution. Yeah. So which means that this is not the same data as the target model. If I'm using different distribution data set, which means that you do not need to know the target model's training data set distribution. Yeah, which means that because in many cases, when you do the attack, all you face is online machine learning API. You can only throw the image in, you get output. Yeah, you have no way to figure out, let's say, what data set Google is using to train the model. Okay, we can come back to this later. Yeah. So now I'm talking about our next work. So that is right now. So all our membership inference attack is based on the assumption that the target model will only give the posterior, the full posterior output for your query image, right? So I give 80% panda, 10% dog, 10% cat. In many cases, the target model will only give you the label, which is panda. Yes, it didn't tell you how confident the model thinks this is a panda or not. In this case, we call it label-only membership inference. In this case, can we still do membership inference attacks? So this is actually a new paper that will be presented by in this year CCS in hopefully in CCS in November in Seoul. This is also done by my PhD student Zhang. So membership leakage in label-only exposures. So how this works? Actually, we developed 2 attacks on this. The first one is called transfer-based attack. This procedure is quite similar to the previous attack, but what we do is following. So we first assume this is a target. We have a data set on our hand that belongs to the attacker. And then this data set, you can assume we do not have the label of the data set, but you can also assume it, but we just do not use this label at all. And then we use the data set to query the target model. And target model will automatically label data set for me. Right? Throw image tell me this is a panda. Throw image tell me this is a dog. Throw image tell me this is a cat. So I'm using a target model here as a labeler or labeling machine. Yeah. So once I have this, so I get my complete data set with the sample and the label. And then I do the exact same thing. I split by training and testing. I train one shadow model. And then I do all the same procedure. I train the attack model. Here, the input of my attack model, still the largest 3 posteriors. Okay, then to do the final membership inference, remember, I still want to know whether this image, this panda image, is a member or not. What I do is the following. So I throw this panda not to the target model, because target model will only tell me this is a panda. Yeah, it does not give me any posterior. But the shadow model is controlled by me. Shadow model I control by me. I can let shadow model give me posterior of this panda, and shadow model will give me 1. Once I have this, I throw this to the attack model, and the attack model will tell me this is a member or non-member. That's basically how this transfer-based attack works. So you can see that one thing that is tricky here is that actually the target sample has no interaction with the target model. Yeah, but however, the only relies on whether shadow model tell me this is a member or not, which actually this sample is not a member of shadow model at all. So the reason we can do this attack, or the reason there's a connection between the shadow model and the target model, is because I'm using the target model to label the data set to train my shadow model. Okay, so which means this labeling part is essential, which means it observed information from target model to let you to train your own local model. So that's the connection we build here. So that's the first attack we build on if you only the target model give you only labels. The second attack, actually, what we did is we used another very well-studied literature. Actually, many of you guys probably are experts. That is adversarial examples. So adversarial examples, I think this is something that I do not give you a recap. Basically, in general, so you add some noise to the image, and the model will recognize this to a wrong thing. Yeah. For example, let's say I throw the image to target model will tell me this is a panda, and then I do some adversarial perturbation on this panda. I get this still visually imperceptible for us. This is still a panda. However, target model will tell me this is a cat. Okay, so that's what the adversarial example is doing. And what we did, because our goal here is not doing adversarial examples, we're actually using adversarial examples to membership inference. So what we did is actually, for each image, for the image we are interested in whether it's a member or not, we adding adversarial example on top of it to make sure the target model will misclassify it. And then once this model is misclassified this image with the noise I add or with the adversarial perturbation I add, I can simply see if the adversarial perturbation is bigger, then I consider this is a sample. I consider this as a member. So in another way, so if a member sample, so in another way, member sample is much harder to be perturbed compared to non-member samples. Yeah, this perturb is an adversarial example way of perturbation. Okay, so basically that's the that's the simple logic for how this attack works. Let's quickly see some experimental results. So here, so the blue bar here is the MNIST attack, which as I proposed, when the attack model only have the full posteriors, have the 3-dimension posteriors, and this green bar here is actually the transfer-based attack, the first transfer-based attack. And the red bar here is the adversarial perturbation attack. You see, in all the 6 data sets we tried, each data set we try actually 5 different models, 6 different models. And these models are actually trained with different overfitting levels. We train with different number of epochs. Yeah. So in general, you see that in many cases, our green and red bar performance is comparable with blue. In many cases, even better. In many cases, it actually is even better than the blue bar. Yeah. This basically shows that actually adversarial examples can be used as a tool to launch membership inference attacks. So right, so this slide is basically because our second attack is using the perturbation-based membership inference attack. Adversarial perturbation-based membership adversarial example-based membership inference attack. So for doing adversarial examples, you need multiple queries to target model, especially our target model here is a black box. Yeah. So here, this figure shows that if you are querying around 2,500 times, basically you are able to get a pretty good performance. Yeah, I mean, this one is still high. This one is still high. So now we are working on more tricks to reduce this number. Right. So now I get 2 more questions. How do you find the adversarial noise without having access to target model? Okay, so this is a question by Hidi. So we are basically using the existing attacks on the black box membership inference attack. So basically the attack we use is Cuba and hot scheme something, I guess. So in that sense, we automatically use that tool. So in that sense, automatically find you the perturbation to let the image to a different class. Okay, we have another question. So for Xinyu Wang, in the transfer-based approach, in the query data set necessarily the same distribution with the target. Good question. So the transfer-based attack in our experiment, yes, I assume we use the data set from same distribution. Because the thing is that if you're using completely different distribution data set, the target model is, let's say, only a dog cat classifier. If you give a plane, the target model will probably label you something really weird. But it might be interesting to try if you're using different distribution data set, whether this will work or not. Okay, we have a third question, Zhang Zhao. Is it based on the assumption that a member sample is more likely to have prediction confidence so that it becomes harder? Yes, Yes, you're right. Yes. So basically, it's that a member sample is harder to be perturbed. Yeah. All right. So I will probably already finish the membership inference part. Now let's go to the second part, that is data reconstruction, but in the online learning setting. So again, so I repeat that the data is the key to to develop to drive the development of machine learning models. And actually, another thing is so Sawas, I will answer your question later. Thank you. So another thing is that actually data is being created or generated at any moment. What this means is that even a powerful company like Facebook or Google or Apple, they train a model, maybe 3 days later, their model is outdated because new data generated by user has been created, right? So in that sense, what this means is that you need to update your model. You need to update the model. You need to add the new data to your model to let your model to learn from this new data being generated. And this is the domain of online learning. So what this online learning means is that normally you have the trained model, you treat this trained model as a pre-trained model, then you add new data, you use the same optimization, and fine-tune this a bit for a less number of epochs. Then you get a prediction. Yeah, then you get a new model that is updated with the information from new data. Excuse me, sorry. All right, so this is a basic setting of online learning. Now I'm wondering whether this can constitute a new attack surface. Yeah, so for example, let's say I have a target model. Today I trained, I put it online. So then I use someone use a panda to query the model. The model will tell you, okay, this is 70% a panda, 20% dog, 10% a cat. Let's say tonight, the model owner get new data. Yeah, then it updates the model. It updates its own model. Yeah, if tomorrow morning, if I use the exact same image to query the model, the updated version of the model, what I will get is a different posterior. What I will get is a different posterior. Yeah. So the reason different output, the reason is simply because your model got updated. You get some new data. So we are wondering whether this can constitute a new attack surface. Because the thing is, I have two versions of the model out there. And then for same image to query the model, I get different output. And this output difference, I call it the posterior difference, is solely because the data used to update the data used to update the model. Yeah, so which means can we reverse engineer back? So can we actually use the posterior difference to infer the information of the data set that is used to update the model? Okay, so this basically is a paper that we published last year at Usenet Security 2020. Yeah. So let's talk about some general attack pipeline. So I have a target model, and then assume the attacker has a problem set with, let's say, 100 images or 100 samples. Yeah. And then I query this target model, the first version, I get 100 posteriors. If my target model is, let's say, 3-class classification, I have 100 probing set. In the end, I will have a 3,000. I will have a 300 dimension vector. Yeah, because each will be 3, 3, 3 until 100, right? And then let's say now the model owner use the updating set to update the target model. Next time, facing the next version of the target model, the updated version of the target model, the attacker use the same probing set to query the target model. I will get the 300 dimension posteriors, yeah, because my probing set here is 100 sample inside. So now I basically have two 300 dimension vector. I can calculate the difference or distance between the two vectors. Basically, I'm just calculating the bitwise distance of this 300 dimension vector. I will go to another 300 dimension vector. I can use the first one minus the second one, or the other way around. Once I have this, I can build some encoder and decoder. So encoder, I use the encoder to reduce the dimension to, let's say, 128. And then I build different decoders for different attacks. So actually in this work, we build 4 different attacks. And due to time limit today, I will only talk about the last one. That is how we going to reconstruct every sample in the updating set. Okay, so before I go deeper for how do we do this multi-sample reconstruction attack, let's talk about how the encoder structure. The encoder structure actually is very easy. Remember, my input posterior difference is a 300 dimension vector. So I just put a 2-layer MLP or fully connected layer and reduce it to, let's say, 128, yeah, if I'm not mistaken. So maybe we use 64 in the paper. And then once I have latent code, now it's the question for how do we build the decoder. So to build the decoder, so I will skip this slide. So build the decoders, as I said, so I'm talking about the attack that is multi-sample reconstruction. Multi-sample reconstruction that is really the most challenging attack here. So our general principle, so our goal here is I want to reconstruct every sample in the updating set. Yeah, not just learning a general information about the updating set. So which means this attack is not a model inversion. Yeah. So our general principle for do this attack is we try to learn the distribution of the updating set. Once we get the distribution, we are using this distribution to sample samples out, to sample images out. And these images we consider as the updated samples. So basically nowadays when you learn, when you listen to about we are learning a distribution, the first thing you should come in your mind is so-called GAN, yeah, generative adversarial networks. So what we do actually is 3 steps. We first propose a new way, a new GAN, which we call it the CBM-GAN. So we did not use the original GAN, but we use a new GAN to learn the distribution of the training updating set, the updating set. And then once the GAN is trained, we take this generator out, we sample, let's say 20,000 images. Yeah. For example, here, I assume my updating set is 100 image, okay? And then I'm using this GAN to generate, let's say 20,000, because my generator can generate as many samples as possible. So once I do this, I further do some clustering on top of my generated samples. Then I take each centroid as my reconstructed sample. Yeah, so here I do some clustering, I here do key means. So key means, since my updating set is 100 samples, I do 100 means. Okay, so now the major technique contribution here is how do we build this GAN. So I will give a quick recap of how a normal GAN works. So normal GAN here basically is assembled with 2 neural networks. One is called the generator, the other is a discriminator. So generator input is a Gaussian noise to the generator, and the generator will generate the samples. And discriminator is simply a CNN, or if it's an image domain, it's simply a CNN to do a binary classification. Sorry, not member. The image, the generator generates is real or fake. Yeah, so it's basically what the GAN do. So you see, the goal of the generator is generate images as real as possible. Yeah. On the other hand, the discriminator job is to make sure it can correctly judge whether image is real image or an image generated by the generator. So basically, you have the 2 competing goals here. That is the normal GAN. So what we did is we proposed a new thing called CBM-GAN. So with CBM-GAN, we add a couple more components on the original GAN structure. First of all, we need to have this connection with the updating. Yeah, with the connection updating will come from the posterior difference. And then of course, posterior difference, you go to the MRP to reduce its dimension to, let's say 128. And then I pad or I concatenate the noise and latent vector together as the input to the generator. And then with this generator, I'm just building a new loss on the generator. So this is the new loss. We call it this is the loss actually for the generator for our CBM-GAN. So if you only look at the second part, that is log dx. If you only check this part, this is the same loss function as the original GAN. But what is more interesting is the left part. This is the new loss we added here. Yeah, there's a new loss we added. We call it the best match loss. So what this does actually is for each sample in the updating set, we force the GAN to learn a sample that looks similar to it. So in this sense, my GAN is able to learn samples of the updating set. So just to not get you confused, here the updating set is not really the updating set we want to test on. It's the shadow updating set. Yeah, so I skipped one slide previously, which actually we also need a shadow model, the shadow data set. Also, we need shadow updating data set. Actually, the update actually is a shadow updating, so which means it's controlled by the attacker. So once you have this, and then for each image in the updating set, we simply build a, let's say, MICE loss or L2 distance. Yeah. Once this is trained, we are able to take the generator out. Now, if I'm facing a target model with 2 versions, I generate a posterior difference. Yes, I throw to the encoder. Then I get a latent vector together with the noise. I can keep on sampling from this generator the syntactic images. The syntactic images that used, we believe that they are used to update models. Then we do the clustering, and then we find the centroid as the updating samples. Okay, but the key part is still how do we train the generator? And the key part of training the generator is actually this so-called best match loss. All right, so I will give one slide to quickly talk about some qualitative result. So in general, so I mentioned that here is a it's an MNIST data set. It's not FMNIST, sorry. This is an MNIST data set. So I remember I mentioned that in the updating set, we tried the updating set with 100 images inside. So on these slides, I have actually 200 images. Okay, all the first columns are the original samples, and all the second columns actually is the ones that we constructed by CBM-GAN. You know, here the goal we try to do here is just reconstruct samples that look similar to that. Yeah, in this, you see, in many cases, it looks quite similar. So we are not just learning what a 2 looks like, or what a 9 looks like, or what a 7 looks like, but instead we are, to some extent, able to learn what the data set itself looks like. So this, of course, this is still a lot of space to improve over this CBM style model, CBM-GAN style model. But we believe that this result give us very positive signals that to construct the training data set of a model from the distribution to, let's say, to samples can be probably a promising way to solve this final problem, right? Because from distribution, which means from the generator to sample images out and to use the image to reconstruct image to reconstruct the target model, the training data set, we believe is a promising direction. All right, so now I have also some time for some questions before I go to the last topic. So some of the questions still on membership inference. Let's assume we have a harder task like hate speech detection where we have a lot of samples classified. So the existing membership inference, most of the subject samples will be classified as being not part of original URC. If they are, yes, Sava, thanks for Sava's very in-depth and insightful question. Actually, this is basically true. So most of the current membership inference, first of all, is on the image data set. Yeah, so there are, to my knowledge, is only one work on the NLP models. It's also by actually Songjeng Song and Vitaly Shmatikov in KDD 2020, if I'm not mistaken, or 2019. So, but in general, so if your data set, even on the image setting, if your data set have so many samples, it's very likely your membership inference performance will drop. And for NLP model, also it's a different story because NLP model is not like each of your training samples is in the same size. Each of your training sample in the same size for image classifier because your image is also always like, let's say 32 times 32, 64 times 64 times 64. But however, for a natural language, your sentence can be long, can be short. So in that sense, that would be a very good question. And I guess that will be a still open domain questions. Yeah, thanks a lot, Savas. More questions on data reconstruction. So I have to mention one thing, data reconstruction till today is still an open problem. Yeah, so there's some works that are able to reconstruct images, only 80 images for a single batch, if your batch only contains 80 images. But to construct the whole data set, if your model is trained with a million samples, I don't think anyone have ever succeed. But if someday, if you manage to succeed this, then this will be definitely the final attack, or actually the most important attack for privacy against machine learning models, for privacy risks of machine learning models. How do I assume that assess? Yes, so similarity of this. So this is a question from Chang Yu. So to assess the similarity, so what we did is we simply measured MSE. So this image I showed on these slides, yeah, this is after the Hungarian algorithm, the matching. Because eventually I'm constructing a set. Set has no order. So I'm just using Hungarian algorithm to actually make the show here. But eventually our output is just a set of a set of images, and to see whether the image is closer to anyone in the updating set, we simply use MSE loss. But you could, or L2 distance in another way. So you could basically use the other kind of loss to compare similarity of images. All right, so now I think I do not have that many time left. So let me go to the last part of the talk. Right, that is a link stealing attack against GNNs. Now let's forget about the image classifier. Let's go to a new kind of a classifier. That is graph neural networks. So on the left is a normal, let's say, multi-layer perceptron or normal CNN, yeah, which is we call it DNN here. So how do you train a DNN? Basically, you have some training samples. For example, you can use this first 3 as the training sample, use the second 2 as the testing samples. Yeah, each of them is has an assumption that this is IID distributed. Yeah, they're IID. So in that sense, you just train them, separately, and then fit to the model one by one, and then you train a model. This is a normal DNN. For example, LSTM, transformers, CNN, MLP are all like this. So on the right side, we have this GNN model, graph neural networks. So this is a new type of neural networks that can handle the graph data. The reason this is necessary because graph data happens all over the world. I mean, many data can be organized in the form of graphs. For example, social networks, location networks, which means your transportation networks, or some molecular structures for protein detection. Yeah, all this data can be organized in the format of graph. So, and if you use the normal DNN to train the data, this data, you will naturally lose the information of the graph structure. So to add the graph structures here together, so this GNN is developed. So basically, I give you a very nutshell introduction about how GNN works. So especially the transductive GNN. The first GNN model was probably proposed in 2017.
Yeah, you dropped. Oh, you have problems with your headset. I see. Okay.
Hello? Yes. Okay. Sorry. So
yeah.
My headset just lost the power. All right. So on the left side is the transductive GNN, which is the first work in graph neural networks called the graph convolutional neural networks, graph convolutional networks. So what this works, how this works is that following. So you have a graph, yeah. Each node has the feature vector. Each node has a feature vector. Each node also has a sample. Sorry, each node also has its label. Yeah, has its own label. So we assume we know 3 nodes label, like a panda, cat, dog. We are interested in the label of the blue node and the red node. To train this, why is it called transductive setting? To train this, we throw every node's features into the model. We throw every node's feature into the model. Yeah, not necessarily including the features. Let's say including the feature of the blue node and red node. Okay, we threw all of them in transductive setting. And then in the prediction phase, once my model is trained, so my goal here, I still want to know the label. I still want to know the label of blue node and the red node. So I just throw the blue node inside with just the ID is enough because its features has been shown. Its feature has been already seen during the training process. And then the model will tell me the posterior of this. Let's say a 70% chance this blue node is a panda. And then to get the red node, you can again throw the ID of the red node inside to the GNN, then tell me, okay, so 70% chance this is dog. That's basically how transductive setting GNN model works. So inside how this loss function, how the model architecture works, I would recommend you to read the original paper of this GCN. So it's also very nice blog about this. Actually, it's a very fun and classical paper to read. So here, you see the goal in the testing phase, I throw a node, GNN will tell me this is 70% panda or dog or cat. So my goal here is or my research question here is, now I give you 2 nodes. Yeah, I'm facing a black box GNN model, it's trained. Yeah, I give you 2 nodes. Can you tell me from the output of that model whether these 2 nodes has an edge in between? That's why we call it a link stealing attack. Yeah, so give 2 nodes, the model will give me 2 output. From these 2 output, whether can we judge these 2 nodes has an edge in between? So that is our research question. Actually, this is a paper will be presented at UC Security 2021 in August this year. which is also by my PhD student, Xinei He. So in this work, actually, we study a complete taxonomy of the attack scenarios. So basically, we assume that attacker can have 3 sets of knowledges. The first knowledge is he can assume the attacker has all the features of all the nodes of the training graph, but no graph structure, all the node features. So in that sense, this is the one set of information. The second set of information is the second set of information is only no partial graph of the original graph. Okay, for example, let's say original graph in this shape, and I know the connection between the green, the blue, the orange nodes connections. Or the third possibility, or the third knowledge the adversary can have is a shadow data set. Yeah, the adversary can have is a shadow data set. So these are the 3 sets of images. Each image, 3 sets of knowledges. So each knowledge, the adversary can have it or not have it. Okay, which means a binary choice. In total, we will have 8 different attack knowledge setting, or which means we will have 8 different attack models or attack scenarios. Yeah, depends on what knowledge you have. So for the sake of time, so I will only talk about the 2 simple attacks. The first attack, we assume attacker has no information of all of them at all. All attacker can do is actually throw in a node in, get posterior, throw another node in, get posterior. My goal is want to know whether blue and red nodes are connected. So all we do, since all information I have is the posterior from target model, I can simply calculate, let's say, a cosine similarity over the 2 posteriors. If my cosine similarity is large enough, I believe there is an edge between these 2 nodes. Yeah, if the posterior similarity, or another way, if the cosine distance is smaller enough, yeah, we believe there's an edge between these 2 nodes. Okay, in this sense, this is also an unsupervised attack. And now let's say I go to my next attack, another simple attack, which is attack 3. So now I still don't have node features, I still don't have shadow data set, but I have the partial graph of the original training data set. So with this, since the information I can use is still only the posteriors and the partial graphs. So what I can do is I query the node of the partial graph to target model, I get posteriors, since I know the real connections of these partial graph nodes. So in that sense, I could actually use the posterior difference and the partial graph structure to build a supervised classifier, a supervised link stealing model, which is also binary model. In that sense, my attack model actually is a supervised attack. So these 2 attacks actually, the attack 3 and the attack 0 I just presented are very similar. The only difference is now I have a partial graph. I can leverage the partial graph as ground truth to train a machine learning classifier to do the attack. So let's quickly give some final information of all the, as I mentioned, we did the 8 attacks from attack 0 to attack 7. So larger the idea of the attack, more information attack has. Yeah, so attack 0 has no information at all. Attack 7 has all the 3 set of knowledge it has. So in general, there's a general trend that more information you have, better attack performance. But however, in many cases, for example, attack 3, you have a partial graph information. Many cases is already strong enough. And more importantly, so as I mentioned, so which means among all the 3 sets of knowledges, partial graph contains most important information for you to leverage to do the link stealing attack. More importantly, shadow data set is the weakest. So which means that if the data shadow, you have a shadow data set, maybe not even necessary here. And another thing is actually all the 8 attacks, I mean, at least most of them works better than the traditional link prediction approach. The link prediction approach is I only use the data itself. Yeah, I do not go through GNN, which means better my attack performance than the link prediction, which means, so this data, the performance data means the privacy information that this is GNN leaks, right? Because of my link prediction approach, I did not use any GNN information. I did not use any posterior from GNN. Yeah, so which means if my attack is better than link prediction, which means this only because GNN remembers the link information, and this link information is leaked through the GNN. So I guess I will give a conclusion. So I've talked about 3 things. We did membership inference. So I talked about how to do membership inference in a much simpler setting. which is our NDSS 19 paper. We also talk about how to do membership inference if the target model will only give you one label. So that is our CCS 2021 paper this year. And then I talk about how to do data reconstruction with the CBM-GAN in the online learning setting. And in the end, I discuss about how to actually do the first, to do the attack on to steal links from the graph neural networks. So I guess that's it. So in the last slide, I would like to thank all my collaborators. So some of them actually also contribute to the work that I present today. And without their contributions, all the stuff I did, it would not be possible. I guess that we still have some time for questions. So now it's time. Yes, thanks.
Great, thanks, Zhang. So there are some questions on the chat.
Okay, so
nothing on YouTube.
Okay.
So I'm just gonna give maybe a few more seconds to see if people want to ask questions on the YouTube chat, and then stop the streaming.
Yeah.
But I'll stop the recording now, and please go ahead.
Yeah. Okay. So this question is a very good question. So I have to say this is a really let's say a concurrent work. So we are not aware of this work. So you see the first so this label only membership inference attack. Basically, the idea is they do not have the transfer-based attack, but they also use the adverse example, which is our perturbation attack. I think the two attack ideas are quite similar. And if you go back to archive, so the time that appear archive is